All right, so for this session, I have all the questions here on this Google Slides that everyone should have access to. And I'm just gonna work through these questions on the slides themselves. So anything that's confusing, just let me know. I have said this before, but for this section and for like a lot of the statistics sections, I think it's actually not as important to be able to code it from scratch. Because I know that there are a few labs that they have you like calculate sample variance using the formulas or like calculating specific test statistics from scratch. Whereas like in reality, all of these methods are built in. Like you can just feed it in like the array of numbers and the calculation can be done for you. So because of that, I don't think it's as important to code from scratch. Of course, some people do understand the formulas by coding it from scratch. So it kind of depends on like how you learn best. So yeah, use your judgment for that. But in my opinion, I think coding it from scratch is less important. I think if you're able to understand the concepts without diving into Python, which I think is the case for most people, that's fine. All right, let's get started. So I picked 4 questions, and then the last part is just like a quick like overview of like the formula of binomial distribution. So I have a question from like sets that has the inclusion-exclusion principle. I have permutations with repetition, which is, if you guys have seen, this is the iPhone question with the passcode. There's combinations, which is like, this question has like, if you have 10 pieces of paper, 6 with consonants, 4 with vowels, what's the probability of drawing a particular thing? And then conditional probability. This is more of like a, honestly, like a level 1 conditional probability question, and we're going to get to more conditional probability later in section 17. So yeah, let's just get started with the first question I have here. It's a set question that is also inclusion-exclusion principle. And if we remember, the inclusion-exclusion principle basically is actually, let me just Google it, inclusion-exclusion principle. And there's a formula that hopefully there's an image here. The formula is, let me find a simple version. Here, let's start with this one. The formula is here, that if we want to find the probability of the union of like A and B, it is the probability of A and the probability of B minusing away this center part. And the whole idea behind that is because of this overlapping middle. So that's the inclusion-exclusion principle. It can be expanded to more than just A and B. I think down here, yeah, they talk about it in like C's, you're just minusing away all the intersecting parts that you're double or triple counting. But I think for our purposes, it's just good to know this main one, that probability of A and B, probability of A union B is the individual probabilities of A plus B minus the middle. And a question that you would use this principle is a question like this. So this question says, if we are randomly selecting customers and make notes of whether a customer uses a Visa card or an Amex card, I put MasterCard here, but let's put Amex just so it's correct. And then these are the distributions, and there are 3 questions that follow. So in this situation, we have probability of A is 0.5, probability of B is 0.4, both A and B is 0.25. Now, whenever I see this kind of question where it gives us some version of like a combined probability, like both A and B, I usually start with a Venn diagram because I think visually is just the easiest way to display it. So over here, I just set up the usual Venn diagram. This rectangle box is our entire sample space. So that includes people who have Visas, who have Amex, who have other credit cards, who have no credit cards. So this whole thing is our sample space. So usually when I have this, I start with the 2 bubbles because there are 2 different kinds of cards. And I will start to put these numbers in. So I like to start with the middle, and we'll sort of see why. The middle, both A and B is 0.25. So I filled this middle part up with 0.25. Then they give us the probabilities of A and B separately. And I could go ahead and write, you know, like 0.5 here, and also and then 0.4 over here. But I think this is kind of confusing because this 0.25 already sort of takes into account the point is already taken into account when we're making that 0.5 and 0.4 calculation. So more accurately, what I like to do is instead of doing 0.5, I take 0.5 minus this middle part. So it's actually 0.25. So 0.25 is the probability of this like crescent shape. If that makes sense. And at any time, if you want to ask a question, please interrupt me. So this crescent shape is 0.25. Similarly, on this other side, I would take 0.4 minus 0.25, which is 0.15. And so you can sort of see that if we're looking at A, it's a combination of this crescent part and this middle part. So A is still 0.5 in total, and similarly, B is still 0.4 in total. And so let's add these up really quickly. So 0.25 plus 0.25, 0.5 plus 0.15, 0.65. That means what is not in here, which means like the people who are neither Visa or Amex would be 0.35. And I like to have it set up such that everything already sums up to 1. So it just makes all the future calculations so much more easy to compute. So you can see 0.25, 0.25, and these all will add up to 1. So now we know that people who only have Visas, 0.25, people who only have Amex, 0.15, people who have both, 0.25, and people who have neither, 0.35. One more important thing to note is these probabilities are in relation to the full sample space. So it's not any like conditional probabilities. It's 0.25 out of everybody that has both Visas and Amexes. So now that I've set this up, you'll sort of see that going into the questions becomes a little bit easier. Let me just like move everything a little bit up so we can like do our questions down here. All right, so probability that there's at least one credit card. All right, so let's start. Let's just grab this and make a copy. So since I already have everything laid out here, let me just start by typing, what is the probability that you have at least one card? And at least one card, now you can see that I have everything laid out. It's just this area, right? Everything that isn't neither. So in this case, I'm gonna assume that in this sample, in this world of whatever this world is taken from, there are only Visas and Amex because they don't really mention any other credit cards. So at least one credit card, we're gonna assume that this 0.35 means no credit cards. So at least one card, I would just add up these 3 numbers. It would be 0.25 plus 0.25 plus 0.15, which is 0.65. Or you could do a 1 minus 0.35. Both give you the same numbers. But you can see because I've already given each space in this Venn diagram a number, it's a lot easier to come up with the answers. So probability of at least one card, 0.65. In this case, you can also use the inclusion exclusion principle.
Question?
Yeah, what's up?
So just really quick. So basically, if you hadn't have done just the simple computation ahead, then you would have had to have, you couldn't have just said, because essentially in the middle, the 0.25, that would be like double counting. But because you did some small computation before, now it's not, correct?
Yep, that's right.
Okay.
So actually, I'm gonna like outline that process next, which is using the inclusion exclusion principle.
Got it. Okay.
So here, imagine that we didn't do that at first. The probability that a selected customer has at least one credit card is the same as finding the probability of A union B. I don't have that union symbol, but A union B. And the principle states that that union is equal to the probability of A plus the probability of B minus the probability of A intersect B. So we have all those numbers actually. We already have all these numbers. Probability of A and B was given to us in the question, 0.5, 0.4. And A intersect B, also given to us here, 0.25. So we can just plug in those numbers really quick. Let me just make it on a new line. 0.5 plus 0.4 minus 0.25, which gives us the same amount, 0.65. Yeah, that's right. So either way you do it, I feel like if you don't want to memorize this formula, I would just prefer just drawing everything out. But this is how you would use the IE principle, the inclusion-exclusion principle. Which
so as it becomes more complex in terms of problems, is this process still the best approach in your opinion?
It really depends. You'll see later that I am actually a fan of, like, if you don't have that many outcomes, I actually am for doing it all by hand. Just because I think that by doing it by hand, you sort of at the same time recognize patterns that you can then translate into the formulas.
Gotcha.
So I feel like a big reason why I actually memorize these formulas is because I did a lot of this by hand.
Sure.
And then it sort of translates, but
sure.
Yeah, but that's also like over years of doing that.
Right, for sure. Okay.
Yeah. All right, so that is the first question. The next question, compute the probability that a customer doesn't own any of the mentioned credit cards. So another thing that we see very convenient, we already know that, is 0.35. But if we didn't have that already, it would just be 1 minus them having either of the credit cards. So the probability of, what did they say was the exact words? None of the mentioned credit cards. Several ways you can do it. One, we already know is 0.35, but you can take it as 1 minus the probability of A union B, which we already know is 0.65. So 1 minus 0.65 is 0.35. So we kind of actually did that same calculation before we even dived into the question. So yeah, so that one's pretty straightforward because we already had that number right there. All right, the last part, compute the probability that a customer only owns a Visa card. So again, very, very lucky that we had drawn this all out, but only a Visa card would be this crescent here. So we know it's straight away 0.25. However, if we didn't do this before, we sort of have to like undo the, we sort of will have to undo the inclusion-exclusion principle. So if you want to find out what probability, sorry, it's not the inclusion-exclusion principle, it's something completely different. But if it's probability of only Visa, you know that 0.5 is Visa, but also part of it has other cards, right? So 0.5 here is a customer that owns a Visa, but part of those customers also have Amexes. And so what we want to do here is just take away that portion of people who already own other cards. So very similar calculation to what we did at the very start, 0.5, just taking away 0.25, which is 0.25. But of course, because we already labeled this diagram, we don't really need to do this calculation by thinking of it as like, okay, excluding the people who also have other cards or anything like that. Any questions? Cool. So this is pretty common question, not so much for, I've actually never gotten this kind of question in an interview, but it's a good one to think about. There are actually a few examples of this in the labs, and I think it's just good to get into the practice of like visualizing your probabilities in a diagram like this. But cool. All right, let's move on to the next one, which is permutations with repetition. So this is actually the second part of one of the lab's questions. To set it up, you have an iPhone, and iPhones have like 4-digit passcodes. And on your iPhone, you have like, because you like, I think it was you ate a pretzel or something, and then you actually have the smudges on the numbers 2, 7, and 8. So there are 3 possible numbers. There are 3 numbers that appear in your passcode, but the code is 4 digits. And the idea now is how many possible 4-digit combinations can you make with 2, 7, and 8 with one of the numbers reused? Does anyone want to like clarify this setup? All right, let me just make this smaller so I have space to do a little bit of work. All right, so the way I like to think about this is I like to first set it up without the repetitions, just because the repetitions sort of complicate the issue. So let's start with the scenario where the repeated digit is digit 2. So in order to like negate the repetition, I sort of like to think of it as like, all right, there's 2A and then there's 2B, them being like distinguishable number 2s. So in that case, possible combinations would be 2A, 2B, 7, 8. Another possible combination would be maybe like 2A, 7, 8, 2B. One more, let's do maybe like 8, 2B, 2A, 7. So these are all possible combinations. And 2A and 2B are distinguishable 2s. And so we already know this as like just a regular permutation. How many ways can you arrange 4 digits is just 4 factorial. So let me actually type this. Let's type it like this. All right. And then number of 4-digit, number of permutations, 4-digit permutations is equal to factorial 4. All right. So now that we have factorial 4, now we have to take into account these repeats. So in this case, 2 is being repeated, right? So even though we have these combinations, while we have these combinations, in this factorial 4, we've also counted combinations where the B's and A's are switched. So in this case, we have these numbers, these combinations. So in factorial 4, we've counted this, and we've counted this. We've counted this, and we've counted this, and this, and this. But in reality, these 2 are the same. These 2 are also the same, and these are the same. So essentially what we did is we double counted. We double counted every single permutation, because we were thinking that the 2s can be distinguished, but in reality, we can't distinguish between 2s. So because of that, we want to take into account the repeats. And so we want to take factorial 4, and let me just do this, 4 factorial, and just divide it by 2, because we double counted. We only double counted. More specifically, it should be 2 factorial. Because if we had, let's say, more number 2s, if it was like 2 A, B, and C, how you would account for that, you'll realize that when you have, let's imagine we just had like 3 2s and a 7. So we had 3 2s and a 7, it would be like A, B, C, 7. Each A, B, C will represent a 2. You'll also have B, C, A, 7. You'll have C, B, A, 7. Basically, you'll have 6 different, let's see, is it A, C, B, B, A, C, and C, A, B, yeah. So these, each of the letters represents a 2, but you're basically counting each combination 6 times, which is 3 factorial times. So however many times a digit is repeated, you need to divide your initial factorial 4 by that number factorial. So if there were 3 2s, you would divide it by 3 factorial. But in this case, there are only 2 2s. So divided by 2 factorial. Any questions? All right. Now, one last step. Here in these first 2 steps, we were assuming that the repeated digit is 2. But there's also the possibility of 7 and 8. And so here, all we have to do is think of all the situations where 7 and 8 are the repeated digits. So that actually means that we have to go from this step all over again and then do this step all over again. So if 7 was repeated, it's another 4 factorial over 2 factorial combinations. And if 8 was repeated, it's another 4 factorial over 2 factorial number of permutations. And so therefore, in total, the number of possible combinations with either 2, 7, or 8 being repeated is just 3 multiplied by 4 factorial over 2 factorial, which I believe, or it should be, the answer that you see on the lab for this part. Gotcha. And I think in this question in the lab, this is the denominator, because I think they're like, you only have like 5 chances to unlock a phone. So the answer would be 5 over this value. So total number of 4-digit combinations is this. An equal sign. Any questions on this part? I think with these kinds of questions, it is a very specific way of breaking down the problem, which I honestly think just comes from practice, but yeah, this is how I would break it down. I think there are probably different ways to break it down, but I think, to me at least, this is the way that I understand it the best. All right, no questions on permutations with repetition? Awesome. All right, let's go on to combinations. So let's set up this problem where you have 6 different consonants and 4 different vowels written on pieces of paper in a bag, and you want to draw 5 letters out of the bag. So first question is, what is the probability that you draw exactly 2 consonants and 3 vowels when drawing 5 letters? And then question B is, out of 6 consonants and 4 vowels, so same bag, how many words with 2 consonants and 3 vowels can be formed? All right, let me make this smaller again so there's some space to work. All right, so in this case, let's do the numerator denominator thing. So, all right, let's see, we draw 5 letters. So first we want to find out, all right, how many combinations of 5 letters can you draw from 10? That's actually really straightforward. Number of 5-letter combinations, regardless of what the letters are. It could be like all 5 consonants, it could be 4 vowels, 1 consonant, it could be 3 consonants, 2 vowels, 2 consonants, 3 vowels. Any 5-letter combination, number of 5-letter combinations is equals to 10 choose 5. So it would be like that formula of, let me actually just type the formula somewhere up here. So if you see n choose k, where n and k are different numbers, the formula is n factorial divided by k factorial multiplied by n minus k factorial. You definitely do not have to memorize this. I just have this memorized from like years of doing this. So this is what that formula is. So whenever you're doing this kind of combination, good to like write a Python function to calculate it. It's also built into SciPy, I think, or NumPy. Anyways, that is basically what this means. It means that you're going to put in 5 and 10. Actually, let me just throw that example in there as well. So 10C5 is the same as 10 factorial divided by 5 factorial times 5 factorial. So that's what this number is. And I won't evaluate it here because that's just a big number. All right, so total number of 5-letter combinations is 10 choose 5. and that's drawing 5 letters. So that would be our denominator. Now, what's the probability that you draw exactly 2 consonants and 3 vowels? It's sort of, so let's take a look at the probability of drawing 2 consonants. So it's 2 consonants out of 6 consonants. And that is really actually just 6 choose 2. That makes sense? I have like slight OCD, so I need like the font sizes to be the same. There we go. All right, this is not number. We're not doing comments here. The probability of getting 2 consonants out of 6 consonants, 6 choose 2. And then, sorry, not the probability, number of ways to choose. There we go. That's more accurate. Number of ways to choose 2 consonants out of 6 consonants is 6 choose 2. And then similarly, number of ways to choose 3 vowels from 4 vowels is 4 choose 3. Then all we have to do is just put this together. So what's the probability that you draw exactly 2 consonants and 3 vowels is probability of, let's just call this A because it's question A, is just 4 choose 3 multiplied by 6 choose 2 divided by 10 choose 5. Any questions on this? I think this one is a little bit more abstract, like getting from these drawings to these and also putting this together, but I don't know how else to explain it.
I have a question. How come you multiply for the numerator instead of adding them together? Because you have.
Let me see. Why do I multiply it? It's because you have that many different ways of doing 2 consonants, and every time, so let's say you have like combination 1 of 2 consonants. Combination of 1 of 2 consonants can be with any combination of 3 vowels.
Okay.
And so that's why you're multiplying them together.
Okay.
Yeah, it took me a while to like string that into words. But yeah, so that's part A. So you'll just do this and that's the probability. Let me just make a new text box for part B.
And just to make sure, I had to kind of step out real quick, but the 10 choose 5, that just basically means, well, maybe it doesn't, I don't know, but 10 times 9 down to, but 5, like 10, 9, 8, 7, 6, is that it?
Not exactly. So that's like halfway of it. So doing like the 10, 9, 8, 7, 6,
yeah,
multiplying that is actually a permutation formula. So another different thing is NPK, which is permutations, is n divided by, I think it's n minus k factorial.
N minus k, right.
Yeah, so this part will result in the 10, 9, 8, 7, 6 part, but because we're also dividing it by k factorial, it gets even smaller.
Gotcha.
Yeah, nice. So this this second part is actually very, very similar to the first part. Out of the 6 consonants and 4 vowels, how many words with 2 consonants and 3 vowels can be formed? So what we start with is we already have kind of like parts to this equation. So how many 5-letter words are there? So number of 5-letter words. Sorry, shouldn't do 5-letter. Some number of 2 consonant and 3 vowel words. That's it. So number of 2.
To be sure that when you say words, you don't mean real words, you just mean combinations. You don't actually...
I think so, yeah. Yeah, that's a good clarification. I'm pretty sure, yeah, because they don't tell us what the letters are. I'm pretty sure it means just like basically any like 5-letter combination of things.
Okay.
That's good. That's a good clarification. All right. So number of 2 consonant, 3 vowel words. We can sort of start from here because the number of ways to choose 2 consonants. So the number of like 2 unique consonants from 6 consonants is 6 choose 2. So this is basically, let's say you have B, C, D, F, G, H, B, C, D, F, G, H. The number of pairs of consonants that you can pick out of those 6 is 6 choose 2. That makes sense. Similarly, the number of like 3 vowels, if you have like A, E, I, O, the number of different ways you can choose 3 out of 4 will be 4 choose 3. And so that's the total. Let me just double check this real quick. But I think that should be the total number of words, unless they're taking into account something else that I want to double check really quickly right now. Let's see. Sorry, I just want to make sure that I'm not missing anything. Nice. All right. So this is not the full answer. So this, sorry, let me just like be more clear on what this is. This is the combinations of 5-letter. This is the number of combinations of 5-letter 2 consonant 3 vowel words. And if you remember, combinations, the order doesn't matter. So that case, so let's say if our letters are B, C, D, F, G, H, and A, E, I, O, if we get like the 2C3V combination of, let's see, we have B, C, and then A, E, I. So in this scenario, 6 choose 2 multiplied by 4 choose 3 counts B, C, A, E, I as the same thing as C, B, A, E, I. Does that make sense? Because in this case, we're just talking about combinations, not permutations. So permutations, if we're looking at permutations, these would be different. But because we're looking at a combination, this is the same. So we're looking at 6 choose 2 times 4 choose 3 unique 5-letter combinations. So in this case, are considered the same. Actually, this is clear enough, I think. All right, so now to account for them being considered the same, because we're constructing words, and in words, the order of your letters matter. We have to look at, all right, within each of these, within B, C, A, E, I, how many ways can I arrange that? And so this is back into a permutation. So this takes us back into, actually not permutation, but factorial. Permutation technically as well, but this would be a factorial. So BCAEI can be arranged in factorial 5 ways. Remember, similarly to like this part where you have 4 digits, there are factorial 4 ways to arrange it. If you have, there we go. If we have the 5 letters B, C, A, E, and I, it can be arranged factorial 5 different ways. And so number of combinations is 6 is this. And then number of ways to arrange each combination is factorial 5. Total number of words is those two multiplied together. It would be 6 choose 2 times 4 choose 3 multiplied by 5 factorial. Cool, so that would be your answer to part B. Any questions on this? Nice. Awesome. Moving on to our last problem before I talk about the binomial distribution really quick. This is a conditional probability question, and there are like 4 parts here. So in this question, 2 dice are thrown. And given that at least one of the dice has come up on a number higher than 4, so that means one dice is, or at least one of the dice has to be a 5 or a 6. What is the probability that the sum of the dice is 8? So in the Learn Labs, they actually provide these events. So the events are described as event A is when either I or J is 5 or 6. Event B is when I plus J equals to 8. And then these are the questions that follow. So let's make this a little bit smaller so that we have some space to work. Can make this smaller too. All right. If you need me to zoom in on any part of the question, please let me know. All right. So the way I like to set this up actually is with a table. Doesn't seem very apparent at first, but we'll see. So in this scenario, we have 2 dice, right? And this goes back in. This is like one of the questions that I like to do visually. So let me make this a different color and this a different color and show you how I set this up. And so let's have this be, actually, yeah. Let's have like each of the rows be like dice 1. And then, sorry, each column be dice 1 and each row be dice 2. Technically, it doesn't really matter. So we have 2 dice here. And I'm going to take each of these as like the combination of the dice rolls. So if you're rolling 2 dice, we have 36 possible combinations of dice rolls, right? So in this case, this would be like first dice is 1, second dice is 2, blah, 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 so on and so forth. And then this will be like 1 and 6. This will be like 6 and 1, and this will be 6 and 6. All right, so this is how I set it up that I think is a very visual way of doing it. All right, and then we'll dive more into this diagram as we go through these questions. So the first question that they ask is, what's the size of the sample space? We can sort of see here that with 2 dice rolls, we have 36 possible outcomes because each of these cells is an outcome, and you have 6 possibilities on dice 1, 6 possibilities on dice 2. So 6 times 6, which is 36. So 36 total outcomes, which is your sample space. All right, so next part, what is the probability of A intersect B? So, all right, I sort of like to look at these separately, like A and B separately. So let's start with event A. Event A is when either I or J is a 5 or 6. Because I have it set up like this, I sort of like to see it as, all right, 5 and 6 are, let me just make this yellow. Any of these yellow squares are where I or J is 5 or 6. So in that case, I really just count them up. I count them, I think this comes to what? 1, 2, 3, 4, 12, 12 plus 8, 20. So I know that event A is 20 cells. Now, how many of those add up to 8? That requires a little bit more thinking. So you sort of think about, all right, there's 5 or 6. What with 5 makes 8? Which is, we want to look for this one, 3 and 5, and I think this one as well, 2 and 6. And I think similarly, we want 5 and 3, and then 6 and 2. So the ones that satisfy both A and B, I'm gonna make them green. And so these are the cells that add up to 8. So in that case, the probability of A intersect B is just the number of green cells over all the cells. So it would be 4 out of 36. Questions on that? All right, to just backtrack really quickly, what if I don't have this diagram over here? How am I supposed to come up with A and B? All right, so let's start with A. So for A, I sort of like to think of it using the inclusion-exclusion principle. So the way I do that is I always try and hold one dice steady. This is kind of like a more abstract way of thinking, in my opinion, but imagine that, all right, I know that if I have like my dice 1 being a 5 or a 6, how many outcomes are there where dice 1 is a 5 or a 6? Yeah, that's a better way of putting it. How many outcomes are there where dice 1 is a 5 or 6? And that would be 1 out of 3. 1 out of 3 of the outcomes have dice 1 being 5 or 6. What about dice 2 being 5 or 6? How many outcomes have dice 2 being 5 or 6? That would be also 1/3. And I'm just doing it like, I sort of think of, all right, I only care about, yeah, I think that's the easiest way to put it, right? How many, what's the probability of a dice getting 5 or 6 is 1 out of 3. However, there's a case where you have an overlap because you sort of double count this middle area in making this calculation, because 1 out of 3 is really like, this is the first 1 out of 3, this is the second 1 out of 3. And so via the inclusion-exclusion principle, you need to take away the cells where both of them are 5 or 6. So for both of them to be 5 or 6, you sort of have to think about it like, all right, what's the probability that if you've rolled a 5 or a 6, what's the other probability of the other dice also being 5 or 6? I'm not sure if that's confusing or not, but basically for both of them to be 5 or 6, it's actually the product of their probabilities. So you're actually taking away this part, 1/3 times 1/3, because the probability that dice 1 is 5 out of 6, but for what is the probability of both dice 1 and dice 2 being 5 or a 6 is the multiple of the two probabilities, if that makes sense. All right, which is just 1/3 plus 1/3 minus 1/9, which is equal to, I think it brings us back to 20 out of 36. So let me just like do this properly. There we go. Yeah, so that's A. Oh, which is actually the next part. So let me just undo that and do that here. Nice. Okay, so that's the probability of A. The easier way to do this is, as I mentioned, just draw the diagram and count up the yellow squares. And like these green squares are considered yellow squares as well. All right. Now it says use the above to calculate probability of B given A. I didn't really go into this that much because conditional probability comes back in section 17, but the formula for calculating the probability of B given A is as follows. So probability of B given A is equal to the probability of A intersect B divided by the probability of A. And so given that, it is equal to probability of A intersect B, which is 4 out of 36, divided by probability of A, which is 20 out of 36. Which is, I believe, 0.2. Yeah, there we go. Questions about this part? I sort of think that for questions like this, especially when your sample space is not too big, I think it's easier to like draw a diagram or like something that's just more visual, because you can sort of see that we want to see like what's the probability that the sum is 8, given that at least one of the dice has come up on the number higher than 4. You know that the yellow part here, it's a denominator where it's 20 cells. And out of the 20 cells, 4 of the cells match the condition that the sum is 8. So it's just 4 out of 20, which is 0.2, which is 1 out of 5. Questions on that? All right. All right, we have 10 more minutes. Let's very quickly go through the binomial distribution. Okay, so this is the same problem that I set up last time during study group. Given that you have the probability of 0.8 of making a shot, what's the probability that you make 2 out of 3 shots? And this is the formula. So let's start by like doing this probability manually. If you make 2 out of 3 shots, let's do V for making it and X for not making it. So 2 out of 3 shots, we have 3 different combinations. We have VVX, VXV, and XVV, right? These are the 3 ways you can make 2 out of 3 shots. And then let's find the probability of each. So probability of making a shot, V, is 0.8. Probability of making another shot is 0.8 as well. And then probability of not making one shot because you missed one of them, 1 out of 3, is 0.2. And then because there are 3 ways to do this, we take the whole thing and multiply it by 3. So that's kind of like how this equation comes about. I know this looks a little bit intense, but if we break this down, you can see that there are 3 main parts to this equation. There is the combination part where it's like, here they do, if you ever see like in a tall bracket, 2 numbers, one on top of the other, that's just another notation for a combination. So this like n over x thing, it's just another way of writing the combination. So we have this part first, followed by the part where we have p to the power of x. And then we also have q to the power of n minus x. I'm doing this so that I can do this. There we go. So P is your probability of success. Actually, before that, N is the number of trials that you're doing this. So here we're making 3 shots. So N is equal to 3. X is the number of successes out of N. So in this case, we made 2 out of 3 of the shots. So X is equal to 2. Typically, the number, you'll see X sometimes, you'll see K sometimes. I personally prefer K because X is other variables, but it doesn't matter. P is equal to 0.8 because P is the probability of success. And Q, in other places, you won't see Q, you'll just see it as 1 minus P. But Q is 1 minus P, which is 0.2. And so if we take this equation and we sort of input these numbers, you can sort of see that we're doing this exact calculation here. 3 is actually comes from 3 choose 2. If you evaluate 3 choose 2, it actually comes out to the number 3. And then here we have P, 0.8. And because you have 2 successes, we're going to raise this to the power of 2. And then here your failures, which is 1 minus 0.8, which is 0.2, is your number of failures. And then n minus x is the number of failures. So in this case, is only to the power of 1. And multiplying this together, you get the probability of making 2 out of 3 shots. Does that make sense? So this equation, this is just the probability of success raised to the power of the number of successes. This part is the probability of failure raised to the number of failures. And this just takes into account the number of ways you can fail or succeed out of n. Cool. So I think that this is a really elegant equation. If you were to actually evaluate all of the probabilities of making like 0, 1, 2, or 3 shots, they actually add up to 1 really nicely. That's really awesome because that's like one of the axes of probability, that all outcomes probabilities have to sum to 1. I believe they ask you to do that in the labs as well. But yeah, that's binomial distribution. Any questions?
Yeah, well, why the term binomial? What does that mean?
That's a great question. I'm not sure why. Let's find out. I think it might have to do with like there being a binary outcome. Let's see, distribution. I believe it's because it has like the number of, it's because it has 2, it's just like a dual outcome experiment, and that kind of comes from it. But I actually never really looked into why it's called the binomial distribution. I don't even know. Let's see, does binomial have its own definition? Let's see. Oh, binomial is a polynomial that's the sum of 2 terms. Interesting. All right, I don't know. I'm not too sure why it's called that, but yeah, I should know. But yeah, I just think it's a very elegant one. All right. Any other questions before we close this off? All right, awesome. Well, thank you all for coming in the middle of the day. Study group later at 6 p.m. Eastern will be on hypothesis testing. So I'll see y'all later. All right, bye everybody.